Howdy, this is Mr. Potter. Today what we're going to do is we're going to extend what we talked about last time. Last time we came up with trig inverse derivatives. The idea that I could write the inverse trig function sine inverse of x. And if I want to take its derivative, I end up with 1 over radical 1 minus x squared. I could do the same thing for tangent inverse of x. And that's going to be equal to 1 over 1 plus x squared. And I could do the trig inverse for secant inverse of x. And the derivative of that function would be 1 over the absolute value of x times the square root of x squared minus 1. And we also talked about how with cofunctions, the derivative of cosine inverse, cotangent inverse, and cosecant inverse are going to be the negatives of each of these three functions. So what we're going to talk about today is we're going to go through a couple of applications of trig inverse derivatives. Now these applications come from Paul Foerster's book, Calculus Concepts and Applications. Paul Foerster does wonderful applications. If you get a chance to use his book in your classroom, it's a wonderful book to use. So the first example I've got here, I've got a patrol car that's 100 feet away from the highway, and I've got a truck that's moving towards it. And I've got this angle theta, but I want to take a look at the situation and try and figure out, based on how fast theta is changing, I want to determine the speed of the truck. So the very first thing that I want to deal with is, how can I write a formula for theta? Well, I know that if this distance is x, then I could say that the tangent of theta is equal to the opposite side over the adjacent side. So I've got x over 100, and I can find theta. Theta should be the tan inverse function of x over 100. So what I've got here is I've got a function of theta. Keep in mind that I'm trying to determine how fast the truck is going. So I really need to figure out how fast theta is changing. And so I really want to find d theta dx, the rate of change in theta with respect to x, the distance of the truck. So what I've got here is I've got a composition of functions. My original function, f of u, is tan inverse of u, where u is this x over 100, which is really 1/100th of x. And I'm writing it that way so I don't think to use the quotient rule. Instead, I think of it as a coefficient times x. And so the derivative here would just be 1/100th. And for tan inverse of u, remember the formula is 1 over 1 plus u squared. In this case, u is this function we just talked about. So d theta dx ends up being 1 over 1 plus x over 100 squared times 1/100th. And simplifying this is going to help us later on in the problem. So I'm going to go ahead and do a little bit of simplification now. When I square this fraction, I'm going to square the numerator and square the denominator, but I also want to distribute this fraction across the sum in this denominator. So 100 times 1 would give me 100. And if I take 100 times this fraction, I'm going to end up with x squared over 100. And all of this is over 1. So here's a good formula for d theta dx. So once I have this formula for d theta dx, I now need to think about this in terms of time, because we don't measure the change in distance with respect to the change in another distance. We talk about the change in distance with respect to time. So I don't really want d theta dx. I want to know something about d theta dt, the change in theta over time. Now, according to the chain rule, I know that it's going to have something to do with d theta dx. And I know that I want to get rid of this differential dx, so I'm going to multiply by dx to get rid of the differential. And I want to acquire dt in the denominator, so I'm going to need to divide by dt. So what I notice here from the chain rule is that the change in theta over time is equal to the change in theta over the distance between the truck and the point on the highway times that change in distance over time. But of course, the change in distance over time we call speed. This is the velocity of the truck. And this d theta dx we just found. So what I've got here is I've got d theta dt as a function that I already know, and a value that's going to be very important for me. Also, if I'm the cop, I'm not going to be able to measure this angle very quickly. But if I did have a radar gun and I had a known place on the highway, say a little place where there's a horizontal white line, I definitely could calibrate my gun to figure out what the change in angle over time is from my moving target. So I could calculate what d theta dt is. And let's say for our purposes here, d theta dt, the change in our angle over time, is going to be negative 0.04 radians per second. So if I'm dealing with this change in time, this has got to be equal to my function, the function that we just found up here, the 1 over 100 plus x squared over 100 times dx dt. So what I notice here is that I have a formula that involves dx dt, and all I need to know to make this work is x squared. In other words, if I know what this distance is, then I can calculate how fast the truck is traveling. So let's say for our purposes that this distance is 500 feet. So x for our purposes is 500 feet. So if I take 500 squared divided by 100, I'm going to get this. I have negative 0.04 radians per second is equal to 1 over 100 plus, well, I know that 5 squared is 25, so 500 squared should be 250,000. But if I lose 2 of those zeros, I'm going to have 2,500 times dx dt. And so that means if I want to solve for dx dt, all I need to do is get rid of this denominator. In other words, multiply both sides by 2,600. And so when I do that, I find out that dx dt ends up being 2,600 times negative 0.04, or negative 104. So now I need to think of what are my units here. This is the change in distance over time. So my units should be distance units over time units. And we remember from how we calculated d theta dt, I gave you that as in radians per second. So my time units are in terms of seconds. And I told you that the distance of the truck was 500 feet. So I'm dealing in terms of feet per second. And all that this negative means is that the distance between the truck and where the patrol car is decreasing. It just means that the truck is moving towards us. The negative is really just indicating the velocity. I'm interested in the speed, so I'm really just interested in this 104 feet per second. Now, 104 feet per second, that doesn't make much sense to us. We're used to talking about how fast vehicles travel in terms of miles per hour. So I know that if I want to do some dimensional analysis here, I can get rid of feet because I know that there's 5,280 feet for every 1 mile. And that would eliminate my feet units. And I also know the relationship between seconds and hours. I know that if I have 3,600 seconds, that constitutes 1 hour. And so now I have the units that I wish to acquire are miles per hour. And since 5,280 feet is equal to 1 mile, this fraction is really a 1. The same thing with this 3,600 seconds over 1 hour. That fraction has a value of 1. So multiplying by these scaling fractions don't actually change the value. And when I do this calculation, I find out that I get 70.909 miles per hour. So this is the speed of our truck. Again, remember, I'm ignoring this negative because it's just reflecting that the truck is heading towards us. So just by knowing this d theta dt, which can be read from a radar gun, and having a position from a line painted on a highway targeting another line painted on the highway, which is a known distance, say 500 feet. A police car with a properly calibrated gun can actually determine the speed of an oncoming vehicle. So this is one of the real-world practical applications of using these trig inverse derivatives. Now, of course, the police officer's not doing all these calculations in his head while he's making the traffic observation. The gun is doing the calculations for him, which is why calibration is so important. So I want to take a look at a second example of trig inverse. And again, Paul Foerster has wonderful examples. So we're still on the highway. And if I'm looking at the highway signs, I notice that as I'm far away, the highway signs are going to be very small because the distance between the bottom and the top is very small due to the parallax. As I travel closer, I'm going to notice that this height here is more visually larger. But if my vehicle is very, very close, this height is going to be it's a very steep height, and so I'm not going to see very much difference between the top and bottom of the sign. So of course, I'm really going to be interested in how this theta changes based on x, my position on the road. So first, let's introduce a couple more angles here. I want to talk about this angle here, which I'll call alpha. And I want to talk about this angle here, which I'll call beta. Now, I know that theta is going to be equal to alpha minus beta. And I also have relationships here between this horizontal distance and this vertical distance. Now, I could say that the tangent of alpha is really going to be 50 divided by x. But dealing with this function with x in the denominator is going to make taking derivatives very ugly. So what I want to do is I want to think of this as a cotangent relationship. So the cotangent of alpha would be equal to x over 50. So now I can really think of that as just being kind of a 1/50th of x. The 50 is now just a coefficient instead of dealing with a full-blown fraction. So the total distance here is 50. X is the horizontal distance, and so the cotangent of alpha is x over 50. And similarly, the cotangent of beta is x over 30, because beta is just this bottom distance from the ground to the bottom of the sign. But theta is the difference in this. So I know that theta is going to be the cotangent. Actually, theta is going to be alpha minus beta. So it's going to be the cotan inverse of x over 50 minus the cotan inverse of x over 30. So this is going to give me where theta is. And I want to figure out some type of relationship to how fast theta is changing with respect to my position on the highway. So I'm really looking for d theta dx. How fast is theta changing with respect to my position on the highway? And because cotangent is a cofunction, I know that its derivatives are going to be negative. But there's going to be the same derivative in value as the tan inverse. So it's going to be negative 1 over 1 plus my angle squared times the derivative of my argument, which would be 1/50th. And I'm supposed to subtract negative 1 over 1 plus x squared over 30 times the derivative of my argument, which is 1/30th. And just as before, I'm going to distribute this 50 just to get a little bit simpler problem here. So I'm going to have negative 1 over 50 plus x squared over 50 minus negative 1 over 30 plus x squared over 30. Now, as I get closer to this sign, I'm going to see that this angle theta is going to increase, but it'll only increase to so much, and then as I get closer to the sign, due to the steepness, this angle theta is going to decrease. So I'm interested in this maximum, and one of the things that we'll learn in chapter 4 is that special things happen when I have a horizontal tangent. So I really want to know when this slope is 0. In other words, when is this derivative equal to 0? And so what I'm doing is I'm essentially setting these terms equal to each other. Negative 1 over 50 plus x squared over 50 equals negative 1 over 30 plus x squared over 30. And of course, because I've got these fractions here, it really doesn't matter what the signs are. I can change them both to positive. And I also could cross multiply in this case just to make the fraction a little bit simpler. So I could say that 30 plus x squared over 30 equals 50 plus x squared over 50. And furthermore, I can go ahead and multiply both sides by a quantity. Say 150. That way I can eliminate all of my fractions, because 150 will go into 30 5 times. So I'm going to have 4,500 plus x squared. And over here, when I distribute, 50 is going to go into 153 times. So I'm going to have 7,500 plus 3x squared. And so what I've got here is I've got a formula that I can solve for x. And so I've got 2x squared equals 3,000, or x squared equals 1,500. Now, of course, when I take x, I'm going to get the positive and negative square root of 1,500. But to be quite honest, when my car is over here, the fact that this angle is a maximum isn't really going to be of much help to me if I'm driving. So I'm only interested in the principal root. So x is going to be the square root of 1,500, which is approximately 38.730. And again, because we're talking in terms of 20 feet, 30 feet, and 50 feet, this is also in terms of feet. So this sine is going to appear the highest. This angle is going to be the widest when I'm 38.730 feet away from the street sign. And so these real-world practical applications for our trig inverse derivatives, knowing where an angle is changing and how an angle is changing with respect to a position or with respect to a time. These are part of what we're going to see a lot of in chapter 4 as we start coming through why we're learning all these derivatives. What are the practical uses? This concept here, the idea that a maximum occurs when I have a horizontal tangent, is one of the key ideas of chapter 4, which we'll be talking about in a few lectures. So thank you for watching. This is Mr. Potter. Have a great day.